Hi there, in this video I'm going to explain the function of a function rule, and this is commonly called the chain rule of differentiation. Okay, so let me title this function of a function, or commonly called the chain rule for differentiation. Okay, so let me take a red pen and a ruler, underline this. So let me apply the chain rule for a function of this form. So if I have y equals a ux to the power of n, okay? So let me explain this function. So a outside is a constant and ux here is a function of x, and n also a constant. So where a and n are constants and ux is a function of x. Okay, so let me show you the chain rule, and let me apply it to a function of this type, y equals a ux to the power of n. Remember, a and n are constants, ux is a function of x. Okay, so let me write down the chain rule. So by the chain rule, to calculate dy over dx, so to work out dy over dx, or the gradient function, we need to calculate dy by du and multiply that by du by dx. Okay, so that is what I mean by the chain rule, or the function of a function rule. So let me apply the chain rule to a function of this form, y equals a ux to the power of n, and let's see what we have for the derivative dy by dx. Okay, so first of all, let me do a side calculation and let me calculate dy by du for this function. So y is a u to the power of n, so my u means it's, so u is a shorthand form for ux, so let me write that here, u is ux. Okay, and if I were to calculate dy by du, so if I were to differentiate this with respect to u, okay, we're going to have na u to the power n minus 1. Okay, so using the basic rule of differentiation, multiply by the power, take away 1 from the power. Okay, so dy by dx, so if I replace dy by du by na u to the n minus 1, we're going to have dy by dx, that is na u or ux to the power n minus 1, okay, multiplied by du by dx. So this is the result using the chain rule for when we differentiate a function of the form y equals a ux to the n. Okay? Now I want you to take note that we can only apply this result if a is a constant. So if a is a constant, that is when we apply this result here, the chain rule related result. Okay? If a is not a constant, we need to use another rule, okay, and we're going to see that rule in the next video. But if a is a constant, we can apply this chain rule related result here. Okay, so let me take this forward with some examples. So let me continue on the reverse. So example number 1, let me underline this. Okay, so in this case, question B, and let's find dy over dx. And let's try a number of examples. So firstly, part A, let's differentiate y is equal to 2 into 2x plus 5 to the power 6. Okay? So let's think about this one. Now, the term in front is 2, okay? So, this 2 over here is our a. So, a is 2, a is a constant. So, going back, that means that we can apply this chain rule related result that we've derived. Now, don't memorize this result. So, don't memorize this result here. Just learn what the result is trying to say. So the result is saying first we need to multiply by the power, so n times a gives us this na. Then we subtract 1 from the power, so if we take away 1 from the power, that is how we got this n minus 1. So we're basically using the basic rule of differentiation here to get this term here. But you need to multiply by d by dx of u, and u is this term here, okay? So, going back to this example, Ra is 2 and ux is 2x plus 5. So this 2x plus 5 is ux. So, let's apply that chain rule related result. So dy by dx will be, so remember the idea, first we need to multiply by the power. So 6 times 2 is 12. So 12 into 2x plus 5. And then we subtract 1 from the power. Okay, so remember, first multiply by the power. That's how we got the 12. Then we take away 1 from the power. So it's 6, and let me use a green pen, minus 1. So green pen means take away 1 from the power. But don't forget, we need to multiply by d by dx of ux, and ux is 2x plus 5, okay? So now it's a case of simplifying this. So d by dx of 2x plus 5 is simply 2. So if we simplify, dy by dx, 12 times 2 is 24 into 2x plus 5, and 6 minus the 1 is 5. Okay? So that completes the first example using the chain rule related result. So remember, if this term, the term in front of your function is a constant, you can apply the result, and the result is multiplied by the power. So I've arrowed that in red. Then we subtract 1 from the power, so I use the green pen, and the green pen means take away 1 from the power. But also you need to multiply by d by dx of u and use the term within the brackets. Okay, so let's try another example. So here's the part B. Okay, so part B is, let's differentiate y is equal to, okay, 5 into the square root of 3x plus 7. Okay, so I can rewrite this as 5 into 3x plus 7 to the power of half. So the root is the same as a half power. And by doing this, let's look at the term in front of our function. So the term in front, a, is 5. Okay, so that means we can use our chain rule related result. So let's apply the result. So dy over dx is equal to, so remember, multiply by the power. So in this case, half times 5 is 5 over 2 into the 3x plus 7. Then we take away 1 from the power, so I use the green pen, meaning subtract 1 from the power. So let me be consistent here. So if I take away 1 from the power, it's half minus 1, okay? But you also need to multiply by d by dx of u, and u in this case is 3x plus 7. So multiply by d by dx of our u, which is 3x plus 7. Okay? So now it's a case of simplifying. So dy by dx will be if I differentiate the 3x plus 7 here, I'll simply get 3. 3 times 5 over 2 is 15 over 2 into 3x plus 7, and half minus 1 is minus half, and you could take this forward, so you can rewrite this as 15 over 2, and 3x plus 7 to the power minus half is the same as 1 over the root of 3x plus 7. Okay, so that is the final solution to part B. So, part C. Let's differentiate y is equal to 1 divided by 2 plus x squared squared. So first of all, let me rewrite this as, so if I bring this term in the denominator up, I could rewrite this as 2 plus x squared to the power minus 2. And let's look at this function carefully. The term in front is 1, so a equals 1, and 1 is a constant, so that implies I can use this chain rule related method. Okay, so to work out dy over dx, let's multiply by the power. So dy by dx is equal to minus 2 times 1 here is minus 2 into the 2 plus x squared. Then remember, take away 1 from the power, so we did this twice earlier. So let me use my green pen. So if I take away 1 from the power, it's the minus 2 that we have, minus 1, okay? Then you need to multiply by d by dx of u. U is the term within the brackets, so let's include that. D by dx of u, u is 2 plus x squared, okay? So let's tidy this up. D by dx of 2 plus x squared, that is 2x, and if we simplify this, dy by dx will be 2x from here times minus 2 is minus 4x into 2 plus x squared, and minus 2 minus 1 is minus 3. Okay, and we could rewrite this as, so let me rewrite that as the minus 4x, and minus 3 power will be the same as the 2 plus x squared to the power plus 3. Okay, so that should be the solution for dy over dx for part C. Okay, right. Let's try another example. So here's example number 2. So let me take a fresh page. So example number 2. Let's find the equations of a tangent and normal to a curve. Okay, so in this case, here's an example. Let's find the equations for the tangent and normal to y is equal to, and the curve has equation square root of 4x plus 1 at the point where x equals 2. So let's find the equations of both the tangent and normal to this curve. Y is equal to the square root of 4x plus 1 at x equals 2. So first things first, we only have the x coordinate, we need the y coordinate to work out the tangent and the normal. So let's work out the y coordinate. So at x equals 2, if I replace x equals 2 into the curve equation, y is equal to the root of 4 into x, which is 2, plus 1. Okay? And if we calculate this, 4 times 2 is 8, plus 1 is 9, root of 9 is 3. So that is the corresponding y coordinates. Okay? Now, for the equation of the tangent and normal, we need dy over dx first, and we need dy over dx in order to work out the gradient of the tangents. Okay? So let's work out dy over dx. So y is the root of 4x plus 1. And let's differentiate this. So before I differentiate, let me rewrite that as 4x plus 1 to the power of half. Okay? And let's see which rule we can apply. So looking at this function, the term in front is a, but our a is 1. So a is a constant 1. And since a is a constant, we can apply the chain rule related result. Okay? So let's apply the chain rule related result that we've seen to work out dy over dx. So first of all, let's multiply by the power half. Half times 1 is half, into the 4x plus 1. So 4x plus 1 is our ux term. And remember, we need to take away 1 from the power. So it's going to be a half here. Let's use our green pen. Minus 1. Okay? So remember, I used the green pen, meaning take away 1 from the power, according to this rule. Then we multiply by d by dx of ux, and ux is 4x plus 1. Okay? So let's tidy this up, let's simplify. When I differentiate 4x plus 1, that is 4. So dy by dx is going to be half times 4 is 2 into the 4x plus 1. Half minus the 1 is minus half. And I'm going to rewrite that as 2 over, so 4x plus 1 to the power minus half is the same as 2 divided by the root of 4x plus 1. Okay, so that is dy over dx, the first derivative. Now that we have dy over dx, let's work out the gradient of our tangent. And remember, to work out the gradient of the tangent, you need to replace the x coordinate, which is 2, in dy over dx. Okay, so let's work out the gradient of the tangent. So I normally name my tangent gradient m1. So I name my tangent gradient m1 and the normal gradient m2. You'll see why I do this soon. So let's work out the gradient of the tangent named m1. So m1 is going to be, if I replace the x by 2, okay, in dy by dx, we're going to have 2 divided by the root 4 into x, which is 2, plus 1. Okay? So if I continue, I'm going to have 2 divided by 4 times 2 is 8, plus 1 is 9, root of 9 is 3. So the gradient of our tangent m1 is 2 over 3. Okay? So I have the gradient of the tangent 2 over 3. I have the x and corresponding y coordinates. So we have everything that we need to work out the equation of the tangent. So let's work out the equation of the tangent. So the equation of the tangent at the point x is 2, y coordinate we found, that is 3. So let's use the formula y minus y1, that is equal to m into x minus x1. So since a tangent is a straight line, we can use the equation of the straight line formula, And remember, in this formula, x1 and y1 are the coordinates of the point where the line or the tangent passes through. So our tangent passes through 2 and 3. And in this formula, m, the gradient, is 2 over 3. So that being the gradient of our tangent. Okay? So if I replace this data in our formula, we're going to have y minus y1 is 3. That is equal to m, the gradient of the tangent, is 2 over 3, into x minus x1, and x1 is 2. Okay? So let me expand this. So let me continue on the reverse. So on the left hand side I have y minus 3, and that is equal to, so let's look at this to remind ourselves. So if I expand the right hand side, 2 over 3 times x is 2 over 3x. Let's make a note of that. So 2 over 3x. And also 2 over 3 times minus 2, that's minus 4 over 3. So minus 4 over 3. Okay? So if I take the minus 3, so if I take the minus 3 to the right hand side, we're going to have y is equal to 2 over 3x and minus 4 over 3 plus the 3, okay, that will give us 5 over 3. So that is the equation of the tangent, okay? So that's the first part of the problem done, but we're not finished by all means, and we need to work out the equation of the normal as well. Now, from our theory of tangents and normals, the tangent and the normal are perpendicular to one another, and remember, if two lines are perpendicular to one another, the product of the gradients equates to minus 1. Okay? Now I've named the gradient of the tangent m1, the gradient of the normal I'm going to name m2, and since the tangent and the normal are perpendicular to one another, m1 times m2, the product of their gradients equate to minus 1. Okay? So in this case, since the tangent and the normal are perpendicular, that implies m1 times m2 is minus 1, okay? And m2, so I'm going to name the gradient of the normal m2, that is minus 1 over m1. And remember, m1 is the gradient of our tangent. So we worked out m1. So from an earlier stage, m1 is 2 over 3. So let me replace m1 by 2 over 3. So in this case, gradient of the normal m2, that's going to be minus 1 divided by m1, which is 2 over 3. And if we simplify that, we're going to have minus 3 over 2. Okay? So that being the gradient of our normal. So we have the gradient of the normal, and remember the tangent and the normal pass through the same point, and the point being 2, 3, so the coordinates we found from an earlier stage. So we have everything that we need to work out the equation of the normal. So the equation of the normal at the point 2, 3. So since the normal is a straight line, let's use the equation of the straight line formula, y minus y1, that is m times x minus x1. So x1 and y1, the coordinates of the point where the normal will pass through are 2, 3. And m, so over here, m is the gradient of the normal, and that is minus 3 over 2. Okay, so if I do the replacement of this data in this formula, we'll have y minus y1, that is 3, that is equal to m, the gradient of the normal, minus 3 over 2, open a bracket, x minus x1 is 2, and if we expand brackets, y minus 3 on the left hand side, that is equal to minus 3 over 2 times x is minus 3 over 2x, and be careful, minus 3 over 2 times minus 2 is plus 3. So if I take this minus 3 from the left to the right hand side, y therefore will be minus 3 over 2x, and the 3 here minus of a minus 3, so if you take it to the right hand side, we're going to have plus 6. Okay, so in this case that is going to be the equation of the normal. Okay, so here are the steps in order to work out the tangent and the normal, but in particular here's the method in order to work out dy over dx. So remember, only if the term in front of your function a, if that term is a constant, you can use the chain rule related result that we've derived earlier. Okay, so you can only use this result if a is a constant. If a is not a constant, we're going to see 2 other rules in the next video, okay, for that instant. So that ends the theory along with the related examples, and that also ends this video. So I hope you enjoyed this video. Do related practice questions, and if you did enjoy the video, a like would be very much appreciated, and I hope to see you soon. Thank you.